guys, this is our new unit and our final unit of the year. This is probability. So we are going to take notes on probability. At any point, it's going to be kind of a long video. Feel free to pause and come back to it later and continue your notes later. Your notes and a practice worksheet will be due on Friday. Okay, so let's get started. Probability. You might be thinking, well, we've been doing probability all year. So we know how to find probability for anything that can be approximated normally. So we can do problems like, let's say we're talking about cats. Okay, so if you Google the weight of cats, we know how to do problems like this. The average weight of a cat is 9 pounds, right? And the SD is 1 pound. I currently have a cat. She might pop in here, but if my cat's still growing, let's see what is the probability that when my cat is grown, my cat will be over 11 pounds. Right, we know how to do a problem like that. We draw a curve, blah, blah, blah. Here's 9 in the middle, 10, 11, 12. So we go up and down by 1, and we want to find this probability. So we know how to do these. We use z-scores and normal CDFs. We also know how to do it if, let's say, I have, I don't know, 20 cats. That'd be crazy. I know how to figure out what is the probability the average weight of 20 cats is, I don't know, over 10 pounds. Okay, these kinds of questions we know how to do because our curve, we're looking at now a sample of 20 cats, and so now we're looking at our curve where we would assume that the average of the sample is the same as the population, but our standard deviation changes, so now it's 1 over the square root of 20, and we have this new standard deviation. But again, we just do z-score and normal CDF. We also, well, in this case, it'd be t-score, I suppose, because we have a small sample. So we would use a t-value in t-CDF, but it's essentially the same process. Okay, we also know how to do stuff when we see percentages, when we're like, okay, 33% of all cats, I'm in a cat mood, are black cats. If I work at a shelter that takes in, I don't know, pick a number, let's say 100 random stray cats, assuming that it's independent, what is the probability that, I don't know, over 50 are black cats? Okay, we actually do know how to do problems like this out of a sample of 100, so we're looking at samples of 100. We would assume that 33%, 0.33, are black, but we know that samples vary, and I want to know what's the probability that over 50 are black cats, so I would find that variation, the square root of PQ over N, P Q over N, and then I would figure out, okay, what's my z-score, and then normal CDF. So again, we know how to do these probabilities with normal approximations, but what if we can't model it normally? What if the scenario or the situation can't be modeled normally? That's what we're talking about in this unit. Okay, so we're about to do basic probability without normal approximation. So for example, what I've got here is this beautiful large bowl of candy. I will tell you there are over 300 candies in this bowl, kind of insane. So we're going to be talking about this candy bowl. All right, so in this candy bowl, so take a look at it. So in a large candy bowl, in there I have 112 Kisses, Hershey Kisses. I have 50 Rolos. Rolos are chocolates that have caramel in them, if you didn't know that. And 63 Werthers, which are like just caramels. And 90 Starbursts. So we're going to talk basic probability. The question might be, okay, if I close my eyes and randomly pick one candy, what is the probability I pick a Rolo? Okay, you might be saying, Ms. Shine, this is just a sample and we're dealing with percents. Why can't I model this normally? Well, remember we had conditions for our sample in this normal curve, and this will not pass conditions because we're only picking one candy. Our sample is not large enough to be modeled normally. So in this case, we can't just use percentages and be like, well, I know that a certain 50 out of the total in the population are Rolos, so about 16% are Rolos. If I pick one, what's the probability it's a Rolo? So that would be 100%. Like, it doesn't make sense because we don't have a large enough sample to be able to make this normal curve. So we can't do this normally. How do we do it? You might be saying, Ms. Shine, that's easy. I have this giant bowl. I need to figure out how many in total I have, and then just see how many are Rolos. So yeah, you might have seen this before. So, but maybe you haven't. I don't know. What we want to do is we want to say, okay, well, how many do we have total? What I'm going to make is a T-chart to help organize my thinking. I have 112 Kisses, 50 Rolos, 63 Werthers, and 90 Starbursts. So if I want to know what's the probability if I pick out one candy, it's Rolo. I'm just looking to find all the Rolos over the total. So I need to find how many candies in total do I have. I add these up. 5, 1, 2, 315 total candies in that bowl. So what I am going to point out, though, is I'm looking for probability of Rolo. This is probably some new notation for you. This is just kind of like, remember when you did f of x? You didn't really plug any numbers in. It was just saying probability of Rolo. So f of x was function of x. This is just notation that is often used. So I'm going to use this notation regularly. So the probability of Rolo will be how many Rolos we have over the total. Okay, so that's basic, that's our starting point. How do we find the probability given the total and the number of the desired event? So this is our basic probability. The probability of A is the number of successes, or the number of A's, amount of A, amount of our success, over the total possible outcomes. So amount of A outcomes over total possible outcomes. So the desired event over the total. Basic probability. But now we're going to keep going. So I'd like you now to just come up with, okay, what's the probability of KISS? And what's the probability of, I don't know, Werther's? So pause the video a second, do the calculations yourself, see if you match what I get. Alright, so KISS should be 112 over 315. Werther should be 63 over 315. .3556, and typically with decimals we just do 4 decimal places to be safe. Werther is 0.2, you don't need 4 decimal places. Okay, so I'm going to start making another table. And this table is going to be a probability model. It's just going to show our probabilities and our outcomes. So our possible outcomes are KISS, Rollo, Werther, and Starburst. And we found KISS is 0.3556, Rollo is 0.1587, and Werther is 0.2. Is there a way that I can find Starburst now? If these are all of my possible outcomes, there's no other outcome in my bowl, is there a way that I could find Starburst? So we know that the whole bowl is 100%. So this whole thing should add up to 1 or 100%. So in order to find this missing outcome, we can just say, okay, well, it's 1 minus all of these put together. And you get Starburst, which is 0.2857. Okay, so this is a key point. All probabilities should add up to 1, which means they can never go over 1 unless there's some sort of scenario in which that would make sense. But all probabilities will add up to 1. And so a probability of a given event, just a random event, should never be over 1, and obviously it should never be negative. So whenever you're making a probability model like this where you show all of your outcomes and then your probabilities of your outcomes, the table should add up to 1. If it doesn't, so if a probability model doesn't add up to 1, you're missing an outcome. Just like we saw before, we were missing Starburst. It didn't add up to 1. We were missing an outcome. And it might be other, or it might be none, depending on the scenario. In this case, it was Starburst. Okay, I want you to consider another possible chart we could make from this bowl of goodies. And you might be doing, just looking at like the type of candy. So chocolate, caramel, however you want to call it, and like fruity. And so when I do this, if I look at my chocolates, that's Hershey Kisses and Rolos both have chocolate. So I'm going to say, okay, I have 50 Rolos from before. 50 Rolos and 112 Kisses, so that means 162 out of the 315 are chocolate, 0.5143. And let's say I'm in the mood for caramel. What has caramel with it? Well, that's Rolos and Werther's. That's 113 out of 315. .3587. And then the fruity ones, the only ones fruity in there are the Starburst, which we know is 0.2857. Wait a second, let's check to make sure that this adds up to 1. Whoa, it adds up to 1.15. It's over 1. What do you think happened? You might be saying, Miss Shine, you counted the Rolos twice. You're right, I counted the Rolos twice because Rolos have both chocolate and caramel. Okay, so they're double counted. So subjects in this model are in multiple categories. That's how it could go over 1. Now, we typically don't like it to go over 1. It happens in certain scenarios, and I call it an overlap. And so how I like to describe this, we're going to get some vocab here. This is called non-disjoint when there's overlap. So we make a Venn diagram and we see that the Rolos are in the middle and the two different events are on the side. This is called non-disjoint, is when there's a possibility that you can have both. Okay, there is overlap, you could have overlap. Both. Okay, as opposed to before when we were just looking at the types of candies, that we call mutually exclusive. Or disjoint, not joint, disjoint, not together. Okay, it means they have nothing in common. There's no both. All right, so if I didn't have Rolos in there, these would all be mutually exclusive. Being fruity and having chocolate are mutually exclusive. Well, in this case, I guess if you had chocolate-covered cherries, it wouldn't be mutually exclusive. Okay, so this is just some vocab for you. Non-disjoint, mutually exclusive. Okay, and we'll come back to non-disjoint later when we talk about how we can find probabilities using Venn diagrams. Okay, cool. So now what we're going to move on to are probability rules. So, probability rules. We're going to be using this chart up here to start. So, we know the probability rule in that we know that the probability of a given event, let's call it A, is, that fraction where it's like all A over the total possible. Okay, which is how we got the probabilities here. Kiss, Rolo, Werther, and Starburst. Now, there's a few possibilities in the questions that we want, you might be asking, okay, well, if the probability of A is this fraction, what is the probability of not A? So example, what's the probability of not getting a kiss? So I close my eyes and I randomly pick one out of my jar. What is the probability it's not a kiss? That's the question. I didn't get a kiss, it must be kind of high. So the probability of not getting a kiss will be everything that's not a kiss. So I could add all of those up, but really a faster way and one that guarantees that I'm not leaving anything out would just be to do 1 minus kiss, because everything is 1 and I want everything except kiss. So everything except kiss. So it's like saying 1 minus everything except kiss, which is 1 minus 0.3556 or 0.6444. Okay, and so we call this not A is called the complement. So our first probability rule is called the complement rule. Which is P of not A, and we find that just by saying 1 minus P of A. Okay, that's the complement rule. Pause the video for a second so that you can try finding the probability of not Rollo. Pause the video and try that out yourself. Probability of not Rollo should be 1 minus the probability of Rollo, which will be 1 minus 0.1587. Okay, that's the complement rule. All right, rule 1. Rule 2. What if you might ask yourself, what is the probability of getting a kiss or a Rollo? So we know the probability of kiss is 0.3556, right? And the probability of Rollo is 0.1587. So logically, the probability should go up because you're giving yourself more options. You're saying, I want a kiss or a Rollo. So logically, the probability should increase. The probability should be more than just kiss or more than just Rollo. It should be higher than both of those. So the probability should go up because you're giving yourself more options. You have more successes, more options. So what operation might we use to show that increase? Well, we add. So this is our next rule. It is the addition rule. So if I want the probability of kiss or Rollo, I'm just going to take the probability of kiss plus the probability of Rollo. .5143. Okay, now there's one note though in our addition rule is that these two events, kiss and Rollo, are mutually exclusive. When I pick a candy out of there, and that one candy, I can't get a kiss and Rollo at the same time. It's either a kiss or a Rollo. It can't be both. So they're mutually exclusive, aka disjoint. And so our addition rule has just a little caveat when it's not mutually exclusive. When it's non-disjoint, there could be a little bit of an issue. So we're going to look at probabilities like that before we finalize our addition rule. For example, let's say I was using our scenario in which we were non-disjoint. So that was when we had chocolate, caramel, or caramel, however you say it. Now I don't even know how I say it. And fruity candy. Okay, and we found that chocolate was 0.5143 by looking at the Kisses and the Rolos, which both have chocolate. We found caramel was 0.3587, looking at the Rolos and the Werthers. And then we found the fruity. And we noted that it was non-disjoint because Rolos are both chocolate and caramel. They've been counted twice. So if they've been counted twice and I want to find what's the probability of chocolate or caramel, I think I say caramel, they're not mutually exclusive. So when I add them together, I'm counting the Rolos twice. So what I need to do is undo one of those counts. So I do the probability of chocolate plus the probability of caramel. It says or, just like we saw before, should increase. But we need to make sure that we're not double counting. So we take out one of those counts. So we take out the both, in this case, Rolos. Right, so we're finding the probability of chocolate, which we see as 0.5143, excuse me, plus caramel. But we have to take out that both section. So the both, in this case, is Rolos, which is 0.1587. All right, because we don't want to count it twice, we only want to count it once, so we take away one of those counts. That way we only counted it once. Okay, and you can see that if we were to actually do some work with a Venn diagram. And so this is what we would do to find probabilities if we have a non-disjoint or not mutually exclusive set. You would probably make a Venn diagram to help understand the scenario some more. And when you make this Venn diagram, you're like, okay, here are my two events, chocolate and caramel. That's what I care about here. And I know chocolate is 0.5143, and that refers to this whole circle. And I know that caramel is 0.3587. And that refers to this circle. Okay, and then in the middle is our both, and that's our Rolos, 0.1587. So if I want to find chocolate, but not caramel, just this part, this shaded region right here, I'm going to take this 0.5143 and take away that 0.1587. So this is chocolate without caramel. 0.5143 minus 0.1587. I said caramel again. I don't know what's going on. 0.3556, and that represents chocolate without caramel. And what that is in my bowl, if I remember, is just the chocolate kisses, which is what the chocolate kiss probability is. And the same here. I just want the caramel, not the both section. So I'll take my 0.3587 and subtract the 0.1587, and I get 0.2. Okay, and so now together it makes the 0.513. This whole blue circle is chocolate. So all in all, I have 0.513 or 51% of chocolate in my bowl. And I have 35% are caramel. But if I want to see just caramel, not without any chocolate in it, it's 20%. Okay, and then when I add these three numbers up to find chocolate or caramel, because or means add, when I add all those up, I get the 0.7143. Now you might be asking, okay, this doesn't add up to 1. So that means I'm missing something. Well, that would be not chocolate nor caramel. So the probability of neither is everything else. So 1 minus 0.7143, which is that 0.2857, the fruity starburst. Okay, and you can use this Venn diagram now to answer any question, like what is the probability of just chocolate? That's right here. What is the probability of neither? That's on the outside. And you can use this Venn diagram now to answer questions. So some people like to create a Venn diagram whenever they see like this both idea, this idea that it's non-disjoint. Okay, so essentially what we have here for our addition rule, that's our next rule. It means P of A or B. So or is the key word for addition. And sometimes you'll see it written as P of A or B. This means or. I like to remember this is or because if I just finish it out, it looks like a O. Okay, so P of A or B is P of A plus P of B minus that both P of A and B. And sometimes you'll see this written as this. So P of A and B. And I like to remember that because if I finish it out, it looks like an A. Okay, and just a side note, if it was mutually exclusive like we saw before with the KISS or Rolo, with KISS or Rolo, notice we didn't have to subtract anything, and that's because if it's mutually exclusive, the P of A and B, or the P of both, doesn't exist, right? If it's mutually exclusive, the P of both is 0. There's no both. So why would you subtract 0? You don't have to. Which is why when it's mutually exclusive, you don't really have anything over here. You're just subtracting 0. Okay, so that's our addition rule. All right, now we're going to get to something that you might be more interested in, which is not just pulling one item out of our bowl, but what would happen if I got 3? You know, my favorite might be, I want to know what's the probability they're all KISS. Let's say I'm in a chocolate mood. All right, so we're moving on to our last rule. So I might ask myself, or you might ask yourself, if I pull 3 candies randomly, so I'm not looking, I'm just going to grab them randomly, what is the probability they are all kisses? Now, I know the probability of kiss is 0.3556. So 1 kiss has a 35% probability. Should the probability of 3 kisses in a row be smaller or bigger? Ask yourself that real quick. Should it be easier or harder to get 3 kisses compared to 1 kiss? I think it should be harder to get 3 in a row, right? It's easier. It should be easier to just pick out 1 and it be a kiss rather than getting a kiss, and then another kiss, a kiss, and then another kiss, and then even another kiss. Oh, didn't work. So it should be harder to get 3 kisses in a row. So to make it harder, to make that probability decrease, it's harder to do. So our probability should decrease. So what we do is we multiply. So multiplying decimals will actually make that number smaller because they're less than 1. If you divide, it'll actually make the number bigger. So we multiply to make the value decrease. All right, so this is the multiplication rule. So what I'm saying is I want 3 kisses in a row, meaning a kiss, and then another kiss, and then another kiss. So what I'm going to do is I'm going to draw dashes to represent how many I'm pulling. sampled or sampled. Right, and so I have 3 kisses that I'm gonna pull, and then I'm gonna label my dashes. So kiss, 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 and that means a kiss is 0.3556, 0.3556, 0.3556, and then I'm going to multiply. Okay, so when I multiply, it's like saying 0.3556 times itself, times itself, times itself. I could write that as 0.3556 to the third, up to you. Could multiply across, and I get this 0.0449. It's the same thing as saying 0.3556 to the third power, 0.0449, or 0.045 when you round appropriately. Okay, so this is the multiplication rule. It's when you are looking not just at one item, but at multiple ones, and you're trying to do that and another one, and so it's really the and rule, but I don't know. It's more just about you pulling more than one or looking at more than one in a sample. So that is equal to multiplying. And just a side note, this is if they're independent events, and we'll talk about that later, but it's just multiplication. All right, so we're gonna see a few more examples, and then you guys are gonna try some on your own, and then we'll be almost done. Okay. So some examples, I'm just gonna redraw my chart here. Kiss, Rolo, Further, and Starburst. So I might ask myself, okay, what is the probability of all 3 being chocolate? I just love me some chocolate. So let's say I'm just like in love with chocolate. Both of these are chocolate. So really what I'm saying is Kiss or Rolo, right? I want all 3 of these to be chocolate. So I want to find the probability of Kiss or Rolo. When I hear or, I should think add. So that's 0.3556 plus 0.1587. And so I put that on all of them, because all of these are Kisses or Rolos, which is really 0.5143 to the third, 0.136. Okay. You might get a question like, you might ask yourself, what's the probability I don't get any Starbursts? Okay, I'm okay with anything else. I just don't really feel like Starburst. So I'm pulling 3 again, and I want not Starburst. If we remember, not Starburst is that complement rule. Starburst is 0.287. Not Starburst is 1 minus 0.2857, which is 0.7143. So I'll put that up here, because I want all of them to not be Starburst. And so these are how you do these problems. You might get one where it's like, what's the probability the first one you pick out of 3, we could say of 4, is the only kiss. So now I'm pulling 4, which means I have these 4 dashes, and I know that the first one is a kiss, but it's the only kiss. So none of these are kisses. And I know that kiss is 0.3556. Not kiss is 1 minus 0.3556. And so these are all 0.6444. And then multiply together. 0.0952. All right, and so we do problems like these. Now, all of these, when you see dashes like this implies an order, meaning this dash represents the first one you pull. So if you get a question that's like, what is the probability of 1 out of 3 being a kiss? So it doesn't matter which one. It could be the first one, could be the second one, could be the third one. You have to decide, okay, how many iterations are there of this grouping? So out of 3, it could be the first one, it could be the second one, or it could be the third one. Because when you draw the dashes, it implies a specific order. So if it's saying 1 out of 3 is a kiss, it can be in any order. So I need to think about all the possible orders. Now they're all going to have the same probabilities on top. So it's really just doing this 1, 2, 3 times. Right? It's like saying 0.644 squared times 0.3556, and I'm doing it 3 times. So I'm saying 3 times I'm saying this is okay, or this is okay, or this is okay. So it's like 3 times this probability, and you wind up with 0.443. Okay, we're gonna learn kind of a quick method to do this in the calculator, either next week or the week after that. I have to look at the calendar. Okay, and so that's the multiplication rule. We have one more rule before I let you guys try it, and then we'll be done. Okay, so you try. Before you try, let's try one more rule, and that rule is the at least one rule. So let's say I wanted at least one kiss. I don't care if it's 1, 2, or 3, right? I'm okay with 1 kiss, or 2 kisses, or 3 kisses, or meaning add, which seems like a lot of work because this is 1 kiss. Then I have to figure out all the 2 kisses, and then I have to figure out 3 kisses. Really what I'm saying is I'm okay with everything except no kisses. So it's like saying 0, 1, 2, 3. I'm pulling 3. I'm okay with 1, 2, or 3. I just want to get rid of 0. So it's really saying 1 minus no kisses. So 1 minus not kisses. And I know not kiss is this. Okay. And that will give me 0.733. So that's the at least one rule. So it's saying the probability of at least one A is 1 minus the probability of no A's, of none. Okay, so I'm gonna give you guys some time to try it yourself. So I'm gonna give you just 4 problems here. Let's go with 1 being, if you pull, so all of these are you pulling 4. 1, what's the probability they are all Rolos? 2, what's the probability none are Rolos? 3, what's the probability the second is the only starburst? And 4, what's the probability of at least one starburst? Try these yourselves, pause the video and try it yourself. Pause the video, try these 4 yourselves. Okay, I'll give you some answers. All Rolos, you've got 4, and they're all Rolos, meaning 0.1587 times 0.1587 4 times, so to the 4th power. You get 6.34 times 10 to the negative 4th, which is like this. Okay, non-Rolos means not Rolos 4 times. So not Rolos is 1 minus 0.1587, 0.8413, 1 minus 0.1587, 4 times. And that's 0.501. Okay, the second one is the only starburst, meaning this one is a starburst, and all of these are not starbursts. Which is 0.7143. So it's 0.7143 to the 3rd times 0.2857. 0.1041. Okay, and the probability of at least 1 starburst is everything except no starburst. I'm okay with 1, 2, 3, or 4 starbursts. The only thing I don't want is no starburst. So it's 1 minus 0.7143 over and over and over again, so 4 times. So 1 minus 0.7143 to the 4th power. And so that's 0.7397. Okay. And those are all of our probability rules. We had the complement rule, the addition rule, the multiplication rule, and now this at least 1 rule. Good luck. Just a little bit more here. So far, we've been working with a giant bowl of candy. A giant bowl of candy, so the population was 315. And then we're just drawing a few from that giant population. So our sample is like 3 or 4 pieces. All right, what if I actually only had a small population? So let's say, I apologize for this lighting. I'm not sure what's filtering the light here, but it's kind of cool. Just go with it. So let's say I just had a small population and I was looking at, say, these 14 candies. I think 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 candies. These 14 candies. And this was my population. The bowl doesn't exist. I'm only looking at these 14 and they're in this small little pile here. What if I now had this population, small population of 14 candies, and I draw a few? How will that affect the probability? Let's say I want to find the probability of 3 kisses. Before we took the probability of kiss and multiplied it by itself 3 times, but now let's think about the probability of a kiss right now. Right now the probability of a kiss is 4 out of 14 because there are 1, 2, 3, 4 kisses out of 14 total candies. And so I want 3 kisses, and I'm not going to put them back. If I put them back, it won't be an issue. So let's say I take this candy and then I put it back. It will still be 4 out of 14 the next time, and therefore it will be similar to what we did earlier. But let's say I take out a kiss and I eat it, because duh. Now, what's the new probability for getting a kiss? Well, now there's only 3 kisses out of 13. The total decreased and the number of kisses decreased. And then I get a kiss again, assuming that occurred. Now, I only have 2 kisses out of 12 total. Notice that the probability is significantly changing. 4 out of 14 is 0.2857, whereas in the end it was 2 out of 12. That's only 16%. It changed by like 12%. So a really significant percent. Every time I take out a candy, the total changes. And the probability is significantly affected. This is called 0.28 versus 0.16. Very big difference. This is really a dependence that we're showing here. The probability of one event occurring affects the next event. So the probability of one event is affected by the other. Now, you might think, okay, well, why didn't we use fractions before when we had that really big population? Well, if I did the probability of 3 kisses with the original population, there were 112 kisses and there were 315 total. And let's say I did the same thing where I'm drawing out 1 kiss from my big jar each time, or my big bowl each time. The probability here is 0.355, and the probability here is 0.351. Notice it's still about 35%. The probability hardly changes. So we didn't really need to worry about it when we had a large population. And so this actually explains why we do that that thing where we say n is less than 10% of the population, how that ensures that it's independent. Because what we're seeing is that if we have a large enough population and we're not drawing out very many in our sample, that probability hardly changes. So we don't need to worry about it when we have a large population. But if you have a small population, so the key point here, small population, you need to use fractions. So I'm going to give you a chance to practice a little bit. And then show you the answers, and then that will be it for, this is called without replacement with small populations. And so now we might get a better understanding of this rule that we use to ensure independence. Since we have a large population, and our n is small, we're only picking out 3 from this big population, it ensures some independence. However, up here, since we had 3 in our population, so it was so small, it affected the probability and we saw that it was dependent. So we could try a few here. Try these guys. The probability when pulling 2, both are Rolo. The probability of no Rolos out of 2. And the probability of 3, the first is the only kiss. Could try these. So pause the video, you can try them now, and then I will show you the answers when you resume the video. Okay. Okay, so if these are both Rolo, I guess I need to bring this back. Oops. There were 4 kisses, 3 Rolos, 2 Starbursts, and 5. So there were a total of 14. Now you can pause the video and do your work. But I want Rolo and then Rolo. So there's 3 Rolos out of 14. And then I take one of those Rolos out. Now there's only 13 total and there are 2 Rolos left. And then I just multiply. And you can just type that in your calculator all at once. There goes a Rolo. 3 out of 14 times 2 out of 13. Just all at once like that. You get 0.0329. Okay, no Rolos out of 2, meaning not Rolo and not Rolo. Well, I know that there are 3 Rolos and 14 total, which means that there are 11 that are not Rolos. And then I take one of those out, and so I take one out of the total as well. And then the last one of 3, the first is the only kiss. So this is kiss, and these are not kisses. So the first one's a kiss, 4 out of 14. And then I take that kiss out, there's only 13 left. And how many are not kisses still? Well, I took a kiss out, so there's really still, if there were 4 kisses, there were 10 that were not kisses. There are still 10 that are not kisses left because I took a kiss out. And now I'm taking a not kiss out, so it's 9 out of 12. And I just multiply here. Okay, and so that's how we do it with fractions. So it's without replacement with a small population is when we start using fractions. Okay, that's it. Try that practice either on Khan Academy or in the worksheet first, and then flip and do the other. So you need to do both, but you can decide which one you want to do first.